Hello again, physics friends. We have talked a lot about angular momentum and rotational inertia and linear momentum, and now we want to stitch it all together and do an example problem of a kid jumping onto a merry-go-round. In fact, you've already thought about this problem a little bit. Today we're going to do a more quantitative calculation. In particular, we're going to calculate the final angular speed of the rotating merry-go-round after the kid jumps onto it. Before we start, I'll just put up in the top corner a few things to recall. Number one, for a point particle, we know that the angular momentum is equal to the position vector of that point particle relative to some origin crossed into the linear momentum. We also talked about the angular momentum associated with the rotation about a fixed point. So if you have an extended object, like a merry-go-round, we talked about the magnitude of that angular momentum due to the rotation as being the rotational inertia times the angular speed. Okay. So with those two pieces of information in mind, let's come back to the problem at hand, which is the following. We'll have a kid, and we'll represent the kid as this point particle with mass m, and this kid is running towards the merry-go-round with velocity, rather than writing the momentum, let's say he's got a velocity v naught. Okay. And that velocity, if you extend the line defined by the velocity vector, intersects with the merry-go-round, not through the origin in general, but through some other location. And we can say, in fact, that the separation between the line through the origin and the line of this velocity is some length b. We can assign to the merry-go-round a mass capital M and a radius capital R. And we'll work in a coordinate system defined in the following way. We'll say the x-hat direction is parallel to the velocity, the y-hat direction is in the plane perpendicular to that, and then we'll have the plus z-hat direction out of the page. Okay, and let's be really explicit here. We'll call our system both the kid and the merry-go-round, and our origin, which we need to define position vectors and so on, will be the center of the merry-go-round. And we've indicated that with this purple point right there. We have two pieces of information. We have Newton's second law, or the linear momentum principle, which says the change in the system's momentum is brought about by a net external force. And we have the angular momentum of a system will change in response to a net external torque. As you are asked to think about in the pre-flight, the question is there a net external force on the system? In other words, is the momentum conserved or not? Is there an external torque on the system? In other words, is the angular momentum conserved or not? Okay. It turns out that the linear momentum is not conserved, but the angular momentum is conserved. Okay, and I want you to think about why that is, but we're going to use that as a fact for now. And let's have our goal be, our question at hand that we want to answer is, what is the final angular velocity of the merry-go-round with the kid on it after the kid jumps, lands, and sticks on the merry-go-round? Okay, so just to be clear, this is the top view. The kid's running along, jumps onto the merry-go-round. After he lands on the merry-go-round and the kid will start rotating about this fixed origin. And our goal is to find that. And the tool we're going to use is the fact that the angular momentum is constant. Okay, so the physics principle that we'll make use of is that L of the system is constant. So we'll use that information. to write down the initial and final momenta, and we'll be able to solve for the angular velocity. So first, let's find out what is the initial angular momentum of the system. And to do that, we'll need to say the following. So initially, the angular momentum of the merry-go-round is 0. It's at rest. What about the angular momentum of the kid? Okay, well, we know it's r of the kid cross linear momentum of the kid before landing on the merry-go-round. Well, let's think about that. As this kid is approaching, the kid has a fixed momentum, and the position vector from the origin to the kid will change, but so will the angle between the momentum vector and the position vector. So at which point should we think about the kid and the angular momentum associated with that kid? Well, it turns out it doesn't matter, because as you can see, if m is fixed and p is fixed and there's no torque on this kid, the child's angular momentum cannot change. So no matter where you compute the angular momentum, no matter where the kid is along this path, right up until he or she lands on the merry-go-round, the kid will have the same angular momentum. If that's true, you might as well make your life easier by considering the instant that the kid is just about to land. Why is that easier? Well, at that instant, the kid has the same velocity v naught and has a position vector r, and r and v naught are perpendicular to each other. So r cross p can be expressed very easily as mag r, mag p, times the sine of 90 degrees at the instant right before the kid lands. Okay, so that's convenient. We know the magnitude of r is this length b. Okay, so that part we know. The magnitude of the linear momentum is m times the speed v naught, and the sine of 90 is 1. So initially, the angular momentum of the kid has magnitude bmv. And how about the direction? Well, if we do r cross p, we're doing the right-hand rule. Our thumb points into the board. Into the board is the minus z-hat direction. So prior to the collision of the kid and the merry-go-round, immediately prior to the collision, or any time prior, in fact, the total system momentum is equal to that of the merry-go-round, which is 0, plus that of the kid, which we just calculated, minus bm v naught z hat. Okay. And we've claimed that the angular momentum of the system does not change. So what we can do next is write down the final angular momentum, and we'll equate that with the initial angular momentum. All right, so we need to make a little diagram here, okay? So I am going to take all of these things that we've written so far, and I'm going to move them over, and I'm going to draw the merry-go-round after the collision, okay? So sometime after the collision, the merry-go-round has this origin. Still, we're choosing the same origin. We have the kid that has landed on the merry-go-round. Now this merry-go-round has already started rotating. This kid is some distance b from the center. The kid has mass m, and the merry-go-round, as we already stated, has total mass big M and radius r. Okay. Now, the angular velocity of the kid and the merry-go-round are the same. The linear velocity of the kid is different than the linear velocity at the rim, because the linear velocity will depend on how far away the kid is from the edge. Okay. But when we think about writing out the angular momentum, we have two things: the kid's angular momentum and the merry-go-round's angular momentum. We know that the angular momentum of the merry-go-round is the rotational of inertia times the angular velocity. And what do we know about the rotational inertia for a merry-go-round? Okay, well, a merry-go-round, we're going to model in this case as a cylindrical disc, a solid cylindrical disc of uniform density and mass m. So the associated rotational inertia for this disc is 1/2 mr squared, as long as it's rotating about the center of the disc. Okay, and where did this number come from, or where did this quantity come from? Well, it turns out you recall that the rotational inertia for point particles is defined to be the sum of each mass in the system times the perpendicular distance between each little mass element and the rotation axis, and we sum that up from 1 to n. In the limit of continuous objects, this sum becomes an integral, and when you do that integral for a disk, you end up with a quantity 1/2 mr squared. In general, all of these rotational inertia terms for solid objects like spheres, spherical shells, disks, hoops, and so on will be a constant number multiplied by mr squared. And you can see that rotational inertia must have units of mass times square of length. And so it'll always be something times mr squared. In this case, it's 1/2 mr squared. So we have an expression for the merry-go-round's angular momentum. How about the kid's angular momentum? Kid's a point particle. We're going to treat the kid as a point particle flat on the disk. And this kid is going to be moving with a final velocity. Okay. And we know from circular motion that the angular speed and the linear speed at some point on the disk will be related by speed equals distance from center times angular velocity. Okay. So for the kid, we need to take the cross product of the position vector of the kid with the linear momentum of the kid once the kid has landed on the disk. Here we see that the position vector and the velocity or momentum vectors are perpendicular. So the kid is going to have an angular momentum that's given by the distance, b, times the momentum, mv final, times the sine of 90 degrees, which is 1. And what direction is this pointing? Well, as before, it's pointing in the minus z hat direction into the page, because r cross p, thumb goes into the page. Okay. How about, we didn't specify what direction the angular momentum of the merry-go-round is going in. Well, the merry-go-round is rotating clockwise, and if you use a right-hand rule by curling your fingers in the direction of rotation, your thumb tells you the direction of the angular momentum vector, and that's also into the page. So that's the minus z hat direction. Okay. So we can now write, we have to do one more thing, which is to re-express v in terms of omega. So we can use v final is equal to b times omega final. This gives us that the angular momentum of the kid is minus m b squared omega final. This tells us that the system's final total momentum, angular momentum, will be minus 1/2 mr squared omega final, excuse me, minus mb squared omega final, all in the z hat direction. And that, we're claiming, is equal to the initial angular momentum by conservation of angular momentum. So we can pick up where we left off by moving over to the middle here, and we can say, in this system, we can say that there's no external torque, therefore L is constant, therefore L final is equal to L initial. Okay. So L final is minus 1/2 mr squared omega plus mb squared omega final, oh sorry, that's a minus mb squared omega final, all in the z hat direction, is equal to m v naught b in the minus z hat direction. Okay, so all of these minus signs cancel. We can ignore the z hat terms and just say that these quantities must be equal to each other. And our goal is to find omega f, so we can isolate and solve. We have on the left side omega f times 1/2 mr squared plus lowercase mb squared is equal to m v naught b, which tells us that the final angular speed for this merry-go-round plus kid is equal to mv naught b. That's the magnitude of the initial angular momentum, diluted by 1/2 mr squared plus mb squared. And there you have it. We can digest this result a little bit. If the kid is running straight parallel to the line connecting the velocity vector with the origin and jumps and lands anywhere on the diameter going through the origin in the horizontal direction, that corresponds to b of 0. And if b of 0, we find that omega f would be 0. Is that sensible? Absolutely. If the kid lands on that line, the merry-go-round won't rotate. So you could say case 1, if b is 0, we find omega final is 0. That checks out, no rotation. If you're running on that line through the origin. What other tests can we do? Well, we could say in, let's say, case 2, what if the merry-go-round had no mass? Okay, so it's a rigid object, it'll spin, but let's set big M equal to 0. In that case, omega final would equal to mv naught b over mb squared, and we would get v naught over b. So that's kind of an interesting case where the kid jumps onto the merry-go-round, and the merry-go-round spins at an angular speed that's equal to the kid's initial velocity, or initial speed rather, divided by how far away from the center the kid is. So that kind of makes sense also. We're not losing any of that. We don't lose any, we don't have to share the angular momentum of the kid with the angular momentum of the merry-go-round because the merry-go-round is massless. And then another case you could consider is, what if the merry-go-round was extremely massive? If m of the merry-go-round goes to infinity, we see that the denominator in omega f goes to infinity, and so omega f goes to 0. That also is sensible. If you jump onto a very massive merry-go-round, you're barely going to make it budge at all. So some of these limiting cases are checking out, and you could pursue other ones as well. Okay, but our main goal today was just to do a sample calculation that involved angular momentum conservation and that involved angular momentum associated with the translation of a point particle as well as the rotation of an extended body, in this case, a disk. So looking forward to our next time together, but until then, take care and be well.